Archimedes' principle states that when you submerge an object, at least partially, there's a buoyant force that's exerted on that object. And it goes further, it says that the buoyant force can actually be calculated. The buoyant force is just equal to the weight of the displaced fluid. So, for example, if you were to take a cup like this, and you were to fill that cup with water, and then you were to take some object and suspend it. This is, for instance, a copper block. If you're to suspend it, it's going to take an upward force to suspend it. But if you were to submerge the object, it's also going to take some force to hold it up, but that force is going to be somewhat smaller. That is because there's a buoyant force exerted by the liquid on the object which helps hold it up. Why is Galileo interested in Archimedes' principle? Because, as I mentioned last time, the buoyant force acts to slow down the acceleration of an object falling through liquid. So if you were to take this object, this copper block, suspend it in a pool of water, and then snip the string from which you are holding it, the object would accelerate downward. That is, it would gain speed as it's falling, but that acceleration would be less than the acceleration it would have felt when it was in air. Here's the formula that Galileo describes for the acceleration of an object when you drop it in a fluid is just going to be equal to the acceleration that it would have felt in the absence of the fluid times a correction factor, which is 1 minus the density of the medium or the fluid divided by the density of the object that you're supporting or suspending. So this right here is the acceleration in a vacuum. That is, if you were to suspend this object in a vacuum and then snip the string, how fast would it gain speed in a vacuum? This right here would be the acceleration when dropped in the medium. Okay, and as I mentioned, when the density of the fluid and the density of the object are the same, then this factor right here becomes unity, or 1. So you have 1 minus 1 is 0, and there would be no acceleration. The object would just float there. This is where we left off last time. And so this time what I want to do is do a couple of examples of how to apply this formula. Maybe I should say right away, though, that this formula here, Galileo doesn't precisely explain why this holds. He says that the acceleration is slowed down by the medium, but he doesn't explain precisely why that's the case. We're going to come back to this formula later after we come across Newton's laws of motion, and then you'll see perhaps more clearly how one arrives at this formula. So at this point, you might just look at this as an empirical formula that describes the acceleration of an object falling in a medium. Okay, so let's do a couple of example problems. So here's some examples. What is the speed, or maybe we should say, what is the acceleration of each of the following objects? Objects when dropped. Okay, so let's suppose that we drop an object made of zinc. And the specific, so here's the material. And let's say these are all balls of the same size. And what's the specific gravity of this material? Well, specific gravity of zinc is right around 7, so it's about 7 times as dense as water. So if you drop it in water, what is going to be the acceleration? Well, the acceleration is going to be equal to g times 1 minus, well, the density of water is 1 gram per cubic centimeter. 7 is the specific gravity, or the density of the zinc. And so you get 1 minus 1/7. 1 minus 1/7 is 6/7. So if we use gravity as being 10 meters per second squared, you'd have 60 over 7 meters per second squared. What about if we were to drop an iron object? Well, then the specific gravity would be 8. The acceleration would be equal to g times 1 minus 1/8, or 70 over 8 meters per second squared. So this would be the acceleration. Okay. Let's do a couple more. So nickel. What is the specific gravity of nickel? Well, right around 9. It's about 9 times as dense as water. So G 1 minus 1/9. And that would be, what, 80 over 9 meters per second squared. Notice as specific gravity goes up, it's falling more and more closely to the acceleration that it would have fallen in a vacuum. Aluminum, the specific gravity is about 3, and once again, we can find that the acceleration is 20 over 3 meters per second squared. And let's do one more. Lead, specific gravity is 11, and the acceleration is equal to 100 divided by 11 meters per second squared. These last two I didn't do the calculations, but you can figure that out on your own. Okay, what about this? So this is example 1. What about example 2? Compare the acceleration of a copper ball falling in air, water, and liquid mercury. So compare the acceleration of a copper ball in air, well, let's do air, in water, and in liquid mercury. So whereas in the previous example, I was imagining all of them falling in the same medium but different materials, here I'm imagining the same material, copper, falling in 3 different media. So let's do this. The acceleration in air would be just G times 1 minus whatever the density of air is, divided by the density of copper, which is about 9. What's the density of air? Well, 1 minus, that's about 1/1000th. 9 equals that. And so we could calculate that. I don't have a calculator on hand, so you can see how to do that. What about the acceleration when falling in water? G times 1 minus the density of water, which is 1/9, well, 1, and the density of the copper again is 9. And so we did this one before. It would be 80 over 9 meters per second squared. And finally, let's do acceleration in mercury. Would be 1 minus, what's the density of mercury? It would be, it's about 13 or 14. Let me just use 13/9. This is an interesting one because 1 minus 13/9. 13/9 is greater than 1, right? So we're going to be subtracting a number that's greater than 1. And so we're going to get G times 1 minus 13/9 is -4/9. What does that negative sign mean? Well, it's -40 over 9 if we use 10 meters per second squared for gravity. Notice it's negative. It means it doesn't actually fall at all. It goes up. It's got a negative acceleration. We are interpreting all these positive accelerations as downward, so this we'd interpret as going upward. That is, if you drop a copper ball in mercury, it will not sink to the bottom. It will rise to the top, and this will be the acceleration as it's rising. Okay, so I think you're getting a sense of how the buoyant force affects the acceleration of an object in that medium. Okay, and why don't we stop there? And I think we'll probably go on to chapter 4 next time.